Alright, hello everyone, and welcome to my next video in this series on geography for my grade 10 students. I've called this video Landform Processes, but essentially what it's about is just a little look at the idea that even though we can't feel it, there's always something going on beneath our feet. The world is always in motion in some way. So we're going to look at the structure of the Earth, a little bit on continental drift, a brief summary of what tectonics are about, and what soil is. And this is going to be a lead up to my next video on tectonics, which will get into quite a bit more detail on how mountains are formed and how earthquakes and volcanoes are created. So with that, we will get started. Alright, so we'll begin with the Earth's structure. Now, the Earth's anatomy can be broken down into 5 main parts, and I'll get into a little bit more detail on each of these sections in a minute. First is the atmosphere. Next, we have the crust, then the mantle, then the outer core, and finally the inner core. So the atmosphere also has 5 distinct layers. First, we have the troposphere, which covers roughly the first 12 kilometers. This is the densest part. This is where we live, human beings live, and where weather happens. So rain and tornadoes and snow and wind, cloud formation, all that happens in the troposphere, the first 12 kilometers. Next, we have the stratosphere, which goes up to around 50 kilometers away from the surface. And this is the upper limit of human aircraft, so jet fighters and commercial airliners, things of that nature. It's also where the ozone layer is located. Beyond that, we have the mesosphere, which goes up to about 80 kilometers. And this is where most meteors falling to the ground burn up. So, while you do get the occasional meteor that's large enough that it makes it all the way through the atmosphere and hits the ground, most small meteors that come in contact with the Earth generally get burned up in the atmosphere about this point. Beyond that, we have the thermosphere, and this goes out to around 700 kilometers. This is where the International Space Station orbits, and where the aurorae, the northern and southern lights, happen. And finally, the exosphere, which goes out to a distance of nearly 200,000 kilometers from the Earth, so more than 4 times the diameter of the actual planet. And this is where a lot of our artificial satellites orbit, so things like our GPS satellites and our weather tracking satellites and our internet and communication satellites, they're all orbiting the Earth at this distance. Next, we have the crust. This is the topmost layer of the Earth. It's thinnest at the ocean basins, where it's just 5 to 10 kilometers thick on average, but it can get up to 40 kilometers along the continental plates. The crust is mostly composed of calcium, silicon, sodium, and basalt. And it forms the tectonic plates upon which the continents float over the mantle that lies directly beneath. The mantle is the thickest part of the Earth. It makes up almost 85% of our planet's total volume, and it goes down to about 2,900 kilometers from the surface. It's mostly made up of quartz or silicates, and the heat in the outer core keeps some of it moving constantly in a fluid or semi-fluid state. Scientists believe that the liquid part of the mantle has the consistency of caramel or honey. So it's not like liquid like water, it's a little bit thicker. So something akin to honey or caramel is roughly the thickness, the viscosity, if you prefer, of the mantle. It's the movement of the mantle that drags the continental plates against each other, apart from each other, causing earthquakes, volcano formation, And when mantle finds a gap in the Earth's crust and reaches the surface, we call it lava. Next, we have the outer core. This is a superheated nickel iron layer of fluid that spins between the mantle and the inner core. There's also quite a bit of sulfur mixed in to this layer, and it goes down to goes between 2,900 and 5,200 kilometers below the surface. The temperatures here reach between 2,700 and 7,700 degrees Celsius. As you can see from the diagram, the bright yellow area, that would be the outer core, and the heat of that creates what's called convection currents in the mantle, almost like a boiling in a way, where it heats the mantle. The mantle rises towards the surface, cools as it gets near the surface, sinks back down, and it continues in this cycle of heating and cooling, and it's this constant movement that causes what we refer to as continental drift or tectonic shifting. Finally, we have the inner core, which goes from about 5,200 kilometers to 6,400 kilometers. So this is the middle part of the Earth. Now, science doesn't know for certain, but we believe the core to be mostly a spherical ball of solid iron with small amounts of nickel, silicon, and oxygen mixed in with it. The temperature here is estimated to be around 5,800 degrees Celsius, but it remains a solid because of the pressure. So there's just so much sitting on top of it. The outer core, the mantle, the crust, and this is exerting so much pressure on the inner core that even though it is hot enough for iron and nickel to be a liquid, it stays a solid ball. The rapidly moving outer core spinning around the inner core is also what generates our Earth's protective electromagnetic field. So for those of you that don't know, the EM field, it's this invisible barrier of energy that loops around the Earth between the North and South poles, and it helps to deflect a lot of the cosmic radiation and solar radiation that comes at us from the sun and other areas of space. All right, now a few things about continental drift. First, let's look at Pangaea. So before the world's continents, as we know them today, all of Earth's land area was grouped into a single supercontinent called Pangaea. So all the world's land masses were grouped together to get in one big area with ocean taking up the remaining space around most of the planet. We believe it was created about 335 million years ago from the coming together of many smaller land masses. So Pangaea is probably not Earth's first supercontinent, but it's the most recent, and it's the one that we have evidence to support. For example, if you look at a map, you'll see that it looks like South America and Africa at one time fit very neatly together, and archaeologists have discovered animal fossils from about the same time period in both of those continents, so in both South Africa or South America and Africa, indicating that at one point, whenever this animal had lived, it moved freely back and forth between the land masses when it was one solid piece before it broke off and separated apart. Pangaea existed until about 175 million years ago, before continental drift took hold and began to pull the landmass apart once more. It separated when a swell of magma from the Earth's core rose up and split this larger landmass into several smaller ones. And as activity in the mantle continues beneath the continental plates, the new land masses move away from each other on either side of the Atlantic and change slightly in shape and size as they move. Currently, the continents move at an unnoticeable rate of just 3 centimeters per year. And at this rate, the gap across the Pacific will eventually close, and a new supercontinent will likely form somewhere around 300 million years ago as all the land joins up again on the other side of the planet. I particularly like this little map that I found online because you can see roughly where all today's modern countries are or were at the time of Pangea compared to where they're located now. So you can see where Canada was roughly located, where China was roughly located, Antarctica, Australia, India, Brazil, Saudi Arabia, Mexico. So where their placement would have been in this one big landmass before everything split apart and started separating. This is just a progressive map, a series of progressive maps that just kind of show, okay, so you had the Permian era 225 million years ago, and Pangea is there, and it's all one piece. Then you have the Triassic era around 200 million years ago, and you can see things starting to separate again. You can start to see the difference between North America and Eurasia, and Africa and South America and Australia and Antarctica, and them starting to break apart and move a little further into the locations we're more familiar with. The Jurassic period, right around the peak of the dinosaur area, 135 million years ago. Then we have the Cretaceous period, about 65 million years ago, right around the time of the big meteor impact that wiped out the dinosaurs, and then where the continents are located roughly in the modern day. Next is a little GIF that kind of shows roughly the last 600 million years of continental drift. So how the continents were one large landmass, how they slowly came together and formed Pangea, which is right about here, and then how they began to separate out again and move into the continents that we now know and where their location is. So as I said at the beginning of the video, the Earth is always in motion, and we don't even realize it because it's just, you can't really feel it move. The Earth spins on its axis to create the days. It moves around the sun during the course of the year, but there's always something going on beneath our feet as well. So, for example, magma is constantly pushing its way to the surface. It brings back old rock from the crust and mantle, superheats it, recycles it, and returns it to the surface. The continents shift and move around like rafts on the semi-fluid mantle, collide with each other, they warp, cause earthquakes, build mountains, volcanoes erupt, forcing material to the surface, which then changes the nature of the crust and the land around them. And water flows, evaporates, exerts its force upon the ground, breaking up rock, breaking up the land, moving it here, moving it there, dropping bits here, building up the land here, wearing it down there, and constantly changing the shape of the Earth and what it's made up and how it's made up of. There are three big geological processes that you guys should know about in my class. First is tectonics, and this is the process by which the continental plates of the crust move against, over, or under one another, causing earthquakes, volcanoes, new land masses, mountains, etc. Transitions. This is the transformation of recycled magma into different forms of rock, and what type of rock is created, whether it's something crystal like amethyst or something more utilitarian like limestone, depends upon temperatures, pressures, trace chemicals that are present, and other factors at the time the rock is formed. And finally, hydrology. So the influence of water and the Earth's water cycle on the formation of rock and changes in the Earth's surface. And this includes precipitation, the tides, erosion, glacier movement. So all of these things that are connected to the movement of water across the face of the Earth. That's hydrology. Finally, a little look at soil. Soil is basically the surface covering the earth, of the earth, aka dirt. And you pick it up and you squish it, and it sometimes feels really, really soft. But really, soil is made up of very, very tiny particles of rock with space between them. It just might feel squishy because of the amount of liquid in it or how fine the rock particles are. But that's what dirt is. That's what soil is. It's tiny, tiny pieces of rock. And common soil types include silt, peat, sand, loam, chalk, and the quality of the soil depends on a few things. How much empty space is between the particles, primarily, and how much space there is of that allowing for water, allowing for air, allowing for the growth of microorganisms to break down surface waste and create nutrients, and how much space there is for plants to grow their roots down. So yeah, it's the space between these tiny tiny pieces of rock. So yeah, if it's just right, you get just the right amount of water, just the right amount of air, enough space for roots to really push through, and you'll get really good big plants like trees and food crops. Fertile soil, what we consider fertile soil. But if the particles are more densely packed, like say clay, for example, where you might get a bit of moisture, but quite a bit of moisture, but maybe there's not so much room in between the particles, then there's not as much oxygen there, not as much room for microorganisms. Plant roots have to work a little harder to bury into it, and that soil isn't as good, isn't as fertile. Soil comes in up to 5 distinct layers, or at least as far as this course is concerned, these are the 5 layers we're going to focus on. I've seen websites that describe multiple layers, 10, 12, 20 different potential layers of soil, where you'll have something like topsoil, and it'll be broken down into several subcategories. For our purposes, these are the 5. All right, these are the 5 main layers. These are the ones I want my students to focus on. So first, humus. This is the surface layer of the soil, and it's made up of discarded organic material. So fallen leaves, seeds, animal waste, animal remains, things that will break down over time because of microorganisms and create nutrients for plants. Next, we have topsoil. So this is where those nutrients get to. So a nutrient-rich layer of silt, plenty of space between the particles for water, air, plant growth. Next, we have subsoil. So a mix of more densely packed soil, such as sand or clay, might contain some trace amounts of water and nutrients that have leached down from the topsoil, but not as much airspace, not as much room for root growth. Next, we have groundwater. Again, there are several names for this particular layer. I'm referring to it as groundwater because it's just simpler for my students. And this is a layer of larger pieces of weathered rock, which might also get mixed with accumulated water that's been pulled down from the surface and settled in underground veins. So basically, underground rivers that are mixed in with these bigger chunks of rock and other chemicals and material that have leached down. And then finally, bedrock. So this is a solid layer of foundational rock, and it might be granite, it might be limestone, it might be basalt, it might be sandstone, but this is the layer that makes up the main component of the Earth's crust. So, there might be some cracks in it, but there's no real breaking of it. It's largely a solid piece with very little air, very little water leached into it, if any. Okay. And then here is a simple diagram with the 5 layers that I've just kind of discussed. So humus, the surface, the topsoil, the subsoil, weathered rock fragments, and bedrock. And not all soil is going to contain all 5 of these layers. Some soil types, some areas of soil may only contain a couple. For example, if you look at farmland, you may very well have all 5 of these: a good layer of humus, good topsoil for growing, a pretty decent layer of subsoil for root growth, um, the weathered rock or groundwater area, and then the more solid bedrock below. But then if you get into a desert, you're not going to have the humus layer. You're not going to have the topsoil layer. You're going to go straight to the subsoil, which is going to be largely sand or clay or salt. And then below that, you might have some weathered rock layer, and then the bedrock layer underneath that, right? Tundra, we looked at biomes earlier in the course. You might have a topsoil layer and a subsoil layer, but it'll be largely frozen. So again, no airspace, no room for plant growth, no room for nutrients to leach down because it's all frozen solid. And then you'll have your weathered rock and bedrock below that. So yeah, depending on where you are in the world, the soil, the layers, how they're made up, will definitely vary. Okay. So that is my quick summary on just how the Earth is structured, the different parts, what soil is about, what continental drift is about. And as I said at the beginning of this video, this is essentially a lead up to my next video on tectonics, which is going to get into crust movement and earthquakes and volcanoes and that sort of movement and those sorts of events in a bit more detail. All right, so thank you for listening, and I will catch you in the next one.